So, in the last class we saw that the pulse number P can be written as the product of. So, the pulse number P can be written as the product of three numbers Q, R, S. Q is the number of voltage sources or transformer windings or thyristors in a basic commutation group, S number of basic commutation groups in connected in series, and such combinations there are R in number. So, totally we get a pulse number P equal to QRS. So, we started with Q equal to 1. Now, that was just for the sake of telling you that that is the most obvious circuit. Now, if you go from Q equal to 1 to Q equal to 2, there is a drastic improvement. So, we will consider only cases where Q is greater than or equal to 2. So, here Q is greater than or equal to 2, R is any positive integer, S is any positive integer. So, we have QRS as positive integers. The only constraint on Q is we will consider only values greater than or equal to 2, not 1. So, we have to somehow find the values of Q, R and S for a given value of P. So, what we do is we try to see how the components are utilized. So, we will see that there is a valve, that is a thyristor valve. We want to ensure that the utilization of the valve is maximized. So, we will try to maximize the utilization of the valve, and there is a transformer. See, the voltage source shown in the figure as actually the EMF across the transformer. So, we want to also see that the transformer utilization is maximized. So, both these quantities are maximized. So, what we will try to do is to arrive at some figure of merit which will ensure that transformer and valves are best utilized. We need some definitions. So, one of the definitions that we use is peak inverse voltage, PIV. So, this is actually a valve rating. So, this is one of the valve ratings. So, a valve will have many ratings. So, when I say rating, rating is something which is always giving the maximum possible value. Okay. So, if I want to know what is the peak inverse voltage, so I have to consider different values of Q. That is what we were doing in the last class. So, if I take Q equal to 2, then there are only 2 voltages. Now, for the sake of simplicity, what I will do is I will show these phasors with an arrow having a length proportional to the maximum value instead of the usual RMS value. I mean, this will help us in easily getting the expressions for peak inverse voltage. So, if I have Q equal to 2, then there are 2 voltages which are out of phase, that is the angle between these two is 180 degrees. So, in this case the peak inverse voltage is 2 em. So, if at any instant one of the thyristors is conducting, then the voltage across the other thyristor will be subjected to a peak value of 2 times em. So, that is very straightforward in the case of Q equal to 2. Now, let us go to Q equal to say 3. So, I can again draw the phasor diagram. So, there are 3 phasors, em is the peak value and the angle between any 2 of these 3 phasors is 120 degrees. Now, there are no 2 voltages which are out of phase. I mean, the phase angle is at most, the phase angle difference is at most 120. So, if I take the maximum value of the difference between any 2 voltages, I will get the peak inverse voltage. So, if I try to take any 2 voltages and try to find the maximum. So, the length of the line which is joining this end of the arrow and this end of this arrow will give me the peak inverse voltage. So, I can try to find this. Suppose I extend this line and extend drop a perpendicular here. So, this angle is 60 degrees. So, the peak value in question is this one. So, I want to find the length of this line segment. So, what is the length of this line segment in terms of EM? So, I have to just take one length which is EM sin 60 and the other length is EM plus EM cos 60. So, this is one length, this is another length. So, I just take the square of these two lengths and take the square root. So, this is the peak inverse voltage. So, you can simplify this. So, one can show that this is equal to 2 times EM cos. So, say what I am trying to do is I am trying to finally get it in terms of Q, that is all. So, I have taken a special case of Q here, Q is equal to 3. So, here Q is equal to 3. So, this is pi by 6. So, this can be easily verified. So, though I have written initially the angle in terms of degree, pi by 6 is in radians. So, this can be easily verified. Now, let me just take one more special case before going to the general case. So, if I have Q equal to 4, then if I try to draw the phasor diagram, I get 4 phasors all having a peak value EM. So, in this case, if I want the peak inverse voltage, you just take any two phasors which are out of phase. So, PIV is 2 EM. So, this was the answer we obtained even for Q equal to 2. Now, it so happens that for any even value of Q, we get the peak inverse voltage as 2 EM, because there I can always find two phasors which are out of phase or having a phase angle difference of 180 degrees. Now, how to do for a general odd value? Take any general Q. Now, what I am interested is, though there are Q waveforms, I am only interested in any two waveforms such that I get the peak inverse voltage. So, I have to take two phasors which are displaced, which are having the maximum displacement between them. So, if I try to just show the two phasors which will give me the maximum displacement, then they will not be displaced by 180 degrees. Now, what I will do is I will just extend this straight line along which one of the phasors is located by a dashed line. Now, my interest is the difference between these two phasors. So, if I have properly selected the two phasors, what is the angle that I have shown here? Pi by Q. So, how is this pi by Q? Yeah. So, between any two adjacent phasors, the angle is 2 pi by Q. So, between any two adjacent phasors is 2 pi by Q. So, that is why the other phasor which is coming next to this is having an angle of 2 pi by Q. So, the angle between these two is 2 pi by Q. Okay. So, but I need this pi by Q because I need to find this length. So, what I am interested is in this length. What is this length? So, this is similar to the case of Q equal to 3. So, only in the case of Q equal to 3, we instead of pi by Q, we had 60 degrees. So, we have a general value for the angle here pi by Q. So, in this case PIV is equal to, so if I take a line segment which is perpendicular to the other line segment, then I can use this right angle triangle to find PI. So, what I have here is one side of the right angle triangle is EM sin pi by q. So, I will take the square of this and add it to the square of the other side length of the right angle triangle, that is EM plus EM cos pi by q whole square, and take the square root. So, this can be simplified. So, there is EM square sin square pi by q and EM square cos square pi by q and EM square as well. So, there is an EM square appearing twice. So, 2 EM square plus 2 EM, sorry, this is EM. So, 2 EM square cos pi by q under root. Okay. So, let me take the common factor outside, root 2 EM under root 1 plus cos pi by q. So, in other words, this is root 2 EM. So, this can be written as 2 times cos square pi by 2q. So, finally, I get the expression as 2 EM cos pi by 2q. So, PIV is either equal to 2 EM if q is even, or it is 2 EM cos pi by 2q if q is odd. So, this is one of the valve ratings. Peak inverse voltage is one of the valve ratings. So, we will see how to use this to get some measure of the utilization. But before going to the measure of utilization, we need one more quantity, that is known as the maximum average DC voltage. So, if this is clear, let me move on to the next. Yeah. If at all you want to go to the previous page, you have to just prompt me so that I can go. So, as soon as something is over, I will go to the next page. So, please prompt me if you want me to go back to the previous page. So, this is PIV. I will be using this for getting one of the figures of merit. So, before going to the actual figure of merit, I will design one, I will define one more quantity, that is maximum average DC voltage. So, we have a notation for this. I will use the notation uppercase V with 2 subscripts DO. So, VDO is the notation for maximum average DC voltage. Now, why the adjective maximum is coming here? So, we are using a thyristor. Depending on the firing angle of the thyristor, we get different average DC voltages. Okay. Now, when do we get maximum? So, when the thyristor acts as a diode, as if it is a diode. That means, if I give continuous gate current as if the thyristor, then the thyristor behaves as if it is a diode. So, then I get the maximum average DC voltage. So, how do I get the expression for the maximum average DC voltage in terms of the other quantities which are known? Say, we have a AC voltage in terms of EM, and we have a basic commutation group in which there are Q thyristors or Q voltage sources, and there is a set of basic commutation groups connected in series. So, S number of basic commutation groups connected in series, R number of such series connections connected in parallel. So, can we get the maximum average DC voltage in terms of these quantities? First of all, we have, let me just note down what we have. The quantities that we have in the voltage, we have EM, we have Q as the number of thyristors in a basic commutation group, we have S as the number of basic commutation groups connected in series, and we have R as the number of such series connections connected in parallel. Now, does the maximum average DC voltage depend on all these 4 quantities? No.
Don't depend upon the parallel path.
Yeah, it is irrespective of the number of parallel paths. Okay, so it will not depend on R. So it depends on, it appears it depends on EM, Q and S. So can I get an expression? So what I need to do is I just need to take only one of the parallel paths and use it to find the average DC voltage. All these are connected in parallel. So the voltage across all these parallel paths is one and the same. Okay, so I can take any arbitrary parallel path and try to find the voltage. So what I need to do is I need to take the voltage across each and every basic commutation group and I have to add them to get the effective voltage. Now, there is one simplification possible here. Should I take each and every possible basic commutation group that is connected in series? Should I take each and every basic commutation group connected in series, find the average? Say the point is, okay, let me show one path, one parallel path. Okay, so this box indicates a basic commutation group. So there are S such basic commutation groups connected in series. Okay, so the voltage that appears between this terminal and this terminal is Vd. See, the lowercase v with a subscript d is the instantaneous DC voltage, whereas what I am trying to find is the maximum average DC voltage. Okay. So we gave some name here, 1, 1, 2, 1, and so on up to S, 1. So the first number is the number in the path, and the second number is actually saying that it is the first path. The average across each of them, if added, will give me the total average. Okay. So should I find each and every average? There are S number of average values. All averages are same. All averages are same. So I can find any one average and multiply it by S. Okay. So straight away, let me get the expression for video. So it is S times the average across one basic commutation group. Now, what is the expression for average for one of the basic commutation groups?
It will be it will depend on number of Q, and those many
Yeah,
will be the half.
can I get the expression? How to get the average in terms of, say, it is in terms of EM and Q. S has already come here. See, please note, S has already come. So I should write the remaining expression in terms of EM and Q. So we have an AC voltage source. So what we are talking about is the maximum average DC voltage. So if you look at the maximum average DC voltage, then we get that only if the thyristors operate as diodes. That means so if I take one cycle of the AC side, so I have shown here, say Q is equal to 6. Suppose Q is equal to 6 and this is one cycle. So one cycle means, say, 2 pi. Now each of these widths, what is the length of each of these intervals? 2 pi by Q. So this is 2 pi by Q, this is 2 pi by Q, and so on. Now each of these widths has a part of a sinusoidal waveform. So if you take any duration of width 2 pi by Q, it is a sinusoidal waveform. Now the peak value is appearing exactly at the midpoint of the interval of width 2 pi by Q. So take any interval of width 2 pi by Q, at the midpoint you get the peak. Okay. So it is part of a sinusoidal waveform whose midpoint is such that the peak is coinciding with that. Okay. So the peak of the sinusoidal voltage which is appearing anywhere is having a peak value at the midpoint. Now, the question is, if this is the case, this is the case for maximum. Say the waveform may be different if I am not interested in maximum. Okay, I am only interested in the maximum average DC voltage. So, if this is the condition, how to get the average?
We will integrate with 0 to pi by q.
Yeah. Yeah, one point to note is that this is repeating after every 2 pi by q radians. So, I need not integrate for 2 pi radians, I can just integrate for 2 pi by q radians. Okay. So, if I want the average, just integrate for 2 pi by q radian. So, what is the expression to be integrated? So, of course, it has to be integrated between two limits whose difference is 2 pi by q. So, I have to integrate what?
Em sin theta.
Em sin theta. What if
Sin theta by
yeah, let us take the independent variable as omega ot. Omega ot is the independent variable, it is the angle. Okay. So, peak value is Em. Okay. Now, an easy way is, say I can arbitrarily fix the instant t equal to 0 or omega ot equal to 0. Suppose I fix it here at the peak. Suppose I call this corresponds to omega ot equal to 0, the instant at which peak occurs. Then what is this waveform? It is Em cos omega ot. Okay. So, if I integrate this with respect to omega ot between the limits, what will be the lower limit?
minus pi by.
No, I want to integrate over a duration of 2 pi by q radian. So, if this is 0, I have to integrate from minus pi by q to plus pi by q. So, minus pi by q to plus pi by q, and I want the average value. So, I should divide this by 2 pi by q. So, that is the expression for video. We can simplify this. Okay. So, what do we get if we simplify this?
En sin square pi by q plus pi by q.
Sin square, I mean, if you integrate cos.
Yes. I integrated from sin, like I put omega t 0 as this point.
Okay, irrespective of, I mean, what waveform you are integrating, where you fix the omega t equal to 0, I mean, you get a, I mean, it's the expression for video is independent of where you fix t equal to 0, of course. Okay. So, if you do that, okay, let me just give some more steps. So, it is SQ by 2 pi Em. So, please note that we are integrating with respect to omega ot. So, this will be 2 into sin pi by q. Is that okay? So, just one cancellation of 2 occurs. So, what we get is SQ Em by pi sin pi by q. So, this is the maximum average DC voltage. So, we have defined two quantities, one is the peak inverse voltage and the other one is the maximum average DC voltage. So, if you look at the expression for video, it depends on Em, it depends on Q, it depends on S, but it is independent of R. Okay. Now, we come to the figure of merit, which will help us in deciding the values of Q, R and S for a given value of P. So, one figure of merit is known as valve utilization factor. Abbreviated as VUF. So, the definition is, the definition of VUF is, it is the ratio of PIV, the peak inverse voltage, to VDO. Now, how does this make sense? Now, for a given value of maximum average DC voltage, do I want a lower value of PIV or a higher value of PIV, which is desirable? For a given VDO, what is desirable? A lower PIV, as low a value of PIV as possible, or as large a value? As large. Say you take a large, if you want a large PIV and you get a small VDO, are you utilizing the valve better? I will repeat the question. For a given VDO, suppose I fix the maximum average DC voltage, which is desirable, to have a large value of PIV or a small value of PIV? See, if I want a large value of PIV, I have to spend more. See, if I want a thyristor which has to withstand more voltage, then I have to spend more, it is more expensive. Okay. For a given VDO, I always go for a case where PIV is low. Okay. Yeah, there may be a slight chance of confusion here, because we say that utilization should be maximized, but the factor which is defined here, valve utilization factor, should be actually minimized. Okay. I mean, this is just because it is defined that way. I mean, the books that I refer to actually do this definition. So, I have to minimize VUF if I want to improve the utilization. So, it is slightly confusing. Please note, I want to increase the or maximize the valve utilization. So, that is equivalent to minimizing valve utilization factor. So, that is because of the definition of the valve utilization factor that way. So, for a given VDO, I always want a PIV as low as possible. So, this should be minimized, should be minimized. So, let us try to get the expression for VUF by substituting the expressions for PIV and VDO. So, we have one expression for VDO, but for PIV we have two different expressions. So, one for odd values of Q, one for even values of Q. Okay. So, if I want the expression for VUF, I get 2. So, let me first write the expression for Q equal to an even integer. So, I will straight away write the expression, you can just verify by looking at the expressions for PIV and VDO. It is 2 pi by SQ sine pi by Q, if Q is even. Is that okay? So, see, just in the previous page we got the expression for VDO, and for Q equal to an even integer, it is 2 EM. So, there is an EM in both expressions that gets cancelled. Okay. So, what we get for VUF is this expression if Q is even. So, if Q is odd, of course, here we need to substitute for PIV and VDO and do a small manipulation, or from which we get pi by SQ sine pi by 2Q if Q is odd. Is this okay? Yeah, Q equal to even, it was just substitution. Here just minor manipulation is required to get this. So, we see that VUF is dependent on Q, it is dependent on S, it is not depending on R, it is also not depending on EM, it is independent of EM, it is independent of R. So, VUF depends on or is a function of S and Q. So, irrespective of whether Q is even or odd, it depends on S and Q only. Fine. So, why I am trying to say that it depends on S and Q is, our intention is to select values of Q, R and S for a given value of P. So, whether all choices are equally same or they are different. So, we make the choices in order to minimize VUF. Of course, this is not the only figure of merit that we are looking at, there is one more figure of merit. So, we will try to say how these two figures of merit in fact take the values for different values of QRS. Okay.